Well, hello. Let's make sure my audio is on. Do we have audio? You'll be registered. Okay. Audio. Audio testing. Here we go. Here we got some audio. All right. First order of business is to check out my toolbox. Bear with me. 5 years online so far. More coming. I have several computers open and checking it out. So hang in there, people. Now, which headgear shall I wear today? I think we're going to go with the Scholar. There you go. All right, much better. That's not really working, is it? Let's go the Devil's Horns. That's more appropriate. All right, so as always, to ask questions today, tweet me at Dionangin. Let me see if I can put my Twitter handle up here so you can see my Twitter handle. I apologize for the delay. This is going to take a couple of seconds. There we go. All right, so today we're going to do a very quick lecture. And sorry for the delay again. I've got some errors popping up here. I'll have to see. I have today's going to be a very fast lecture. It's on one topic, and that topic is sample size calculation. Sample size calculation is actually a huge topic. When we do this for real, we usually hire statisticians who go through a day's worth of computations to get us the best estimate of how many people or subjects we need in a study to acquire sufficient power to detect the thing we claim to be detecting. Okay, so as has been hinted throughout this year, the number of people in the study matters. So you remember for like our chi-squared, the number of elements in each cell matters. That determines what tests we can use. It determines the precision of our estimate. Remember when we dealt with confidence intervals? The size of that confidence interval tended to vary with the total n's. If you remember our definition of standard error, it was a standard deviation divided by the square root of n. So the bigger the n, the smaller the error. So in short, the rule of thumb is the more people in our study, the better, up to a certain point, because it's a law of diminishing returns. So we always want to know what is the smallest of people we need to examine or to measure or to study to answer the question that we are proposing. And to do so today, we want to go over some of the very simple concepts we've covered already, and around type 1 and type 2 error and rejection zones and things like that. And if you had any issues from those lectures, now's the time to revisit them. If you don't understand at the end of all this, don't worry about it too sample size calculation, not that much on the underlying theory, but hopefully get some of that as well. So as always, if you want to ask me a question, tweet me at Dionangin. I have other computer open on the side here that I've got streaming Twitter on, and I'm about to start sharing my screen. And when I share the screen, you will see the Google Slides from today's presentation. However, I will point out that the slides are a bit more complex than they have in the past. And as a result, Google is not doing with them as well as they should. And so some of the graphics aren't showing up on this display. However, the version that you have, the PowerPoint slides that you have from the website, contain all of the graphics. I will try as best I can to point out those cases where there's actually graphics in your version that you can't see on this Google version. All right, so let us begin. Let me start by sharing my screen. Screen sharing now. Hopefully this works. I'm going to share this. Right now, I'm going to move up to the top. I thought I want to share. I'll share. The connection is kind of slow right now. I'm going to close that and go back and get me right. Good. So, sorry for the delay. It was really slow right now. So let's share again. We're going to share this. So hopefully you are seeing that's really not working. Okay, let's try this again. Sorry about that. I'm having a hard time here getting the right screen to share. Oh, this connection speed is driving me crazy. That's better. All right. Let me close down some windows. Let's close some windows. Close. Close. Talk amongst yourself for a second. We'll be back in a second. This is a lot like regular class, isn't it? Where I'm struggling with the computer, and you guys just spend time waiting for me to get something done. I'm almost there. I don't know yet. The next NASA Mars mission, because they're actually soliciting publicly suggested experiments. Mars lander, and the deadline for submitting one is today, and I missed the deadline. But you guys should be aware of that. If you're interested in space sciences, NASA has a website called Solve, where they actually invite the general public to participate in suggesting experiments to be included in future space missions. And the winner gets $20,000. That's a sweet gig, but also you get the honor and the pleasure of suggesting an experiment that goes to Mars. So if you're interested, just go to NASA's Solve website. All right, here we go. I'm going to screen share. I'm going to share this piece of work. Yay! Here we go. Okay, it's working, I think. Working. If you can't see this, tweet me right away. So I'll start the presentation. And we are loading. Why is it taking so long? It never takes this long before. Here we go. All right, sample size determination. That is today's topic. Ready to go? Okay, so the slides today were actually taken from a friend of mine, whose name is Dr. Nick Barrowman. He's a senior statistician over at CHIO, the Children's Hospital here in Ottawa, and a good friend of mine. He gave a guest lecture in this class many years ago using these slides and teaching this topic. So I decided to save him the trip downtown this year, and we'll just be using his slides, but not using his body and his voice. So Nick, thank you very much for your exquisite slides. Unfortunately, as I mentioned, Google is not allowing some of the graphics to appear, but those graphics will appear on the PowerPoint slides. So first line of what we'll talk about today, we're going to do an example, and the example is a drug which purports to lower blood pressure. We're going to state our null. We're going to talk about type 1 and type 2 errors, which you guys all know about already. We're going to look at the sampling distribution of the mean. Remember that thing? We talked about that briefly. We're going to go over that again. We'll look at the probability of the type 1s and type 2 errors, and we're going to compute the sample size based upon a simple formula that I will give you. And lastly, we'll look at the famous effect sample size calculations. This stuff down here, sample size from literature, we won't bother with because time is short. So the example we're going to work with today is this. Physicians or epidemiologists or health science students, doesn't matter, but somebody designs an intervention, a drug, let's say, or some kind of therapy that reduces the blood pressure of patients who already have high blood pressure. Does it work? We don't know. So we're going to commission a study. And to do this study, we're going to have to figure out how many people must be recruited into the study to determine if indeed the drug works. And this happens every day, and very often they contact my friend Nick to do the calculation. And this is a simple example of what he does. So if there are too few people in our study, we're not going to detect an effect, even if there is one. Which type of error is that? That's where a guilty man goes free. That's a type 2 error. If there are too many, then you're going to expose people to risk unnecessarily, and you're going to waste money. As I mentioned, there's a diminishing return on investment after a certain number. So why recruit 10,000 patients when you only need 100 to answer the question? Okay, moving on. Now, the null hypothesis here is always there's nothing going on. So here it's, on average, the intervention is associated with no reduction in blood pressure. In other words, the null states that the drug does not work. So we always begin by assuming that the drug does not work. Now, the people who commissioned Nick to do the study, to compute whatever people in need, are assuming that the null hypothesis is false. In their hearts, they think the drug actually does work. So the test is designed to put the null hypothesis to the test, to determine whether or not we can reject it or fail to reject it. By the way, I still hope you're seeing this presentation. We're really sucking if you have the slides very advancing. So here are the various outcomes of the study. Kind of like we talked about in class earlier. We looked at the guilty man, innocent man under trial. So here is what the study findings will determine. That the intervention has no effect. In other words, we fail to reject the null. Nick has put accept the null. He's one of those people. He believes we can say accept the null. I do not believe so. We differ on this point here. But because these are his slides, I left this in. So in other words, here is people who say, or the findings of our results say that the drug does not work. And here, the drug does work. And over here is, in reality, what's the situation? In reality, the drug does not work. In reality, the drug does work. Okay? So if in fact our study finds that the drug doesn't work, and in reality it doesn't work, well, that's good. And if in fact our study finds that the drug works, and in reality it does work, well, that's good too. So these two situations are good, and these two are bad. So here we correctly fail to reject the null, not accept the null. And here we correctly reject the null. Those are good situations. And over here we have our type 1 and type 2 errors. And we've been through this before, right? A type 1 error is when we incorrectly reject the null. In other words, we claim that something works when in fact it doesn't work. And here is a type 2 error where something does work and we fail to find that it does work. And I argued in class that we tend to be more concerned with this, but we do have reservations about this as well. So we work really hard to minimize this, and very often that means this gets larger. So there's a trade-off between the two. So the study population is going to be all the people who would be eligible for this drug. So people who have high blood pressure. We could, in practice, limit that by their age, by their gender, by their accessibility, whether or not their life is at stake, and those kinds of things. So our study participants are, again, a sample from study population. And in this study, we're going to measure their blood pressure at baseline and later on 6 weeks later after they get the drug. And the outcome we care about is the change in blood pressure, right? And so our null is saying that change in blood pressure is 0. Nothing's going on. Change is 0. The drug had no effect on the blood pressure. And this is a mixed little diagram of what a sampling population is. So there should be an image here. I think there's an image in your slides. A random sample of individuals taken from this pot here. And we perform calculations on this random selection. We get a sample mean, and we infer something about the population mean of this population. So to refer back to all the things we've learned about this year so far, this is a statistic, and this is a parameter. We do things with the statistic to learn about the parameter and therefore make inferences about the population. So remember, we talked about this theoretical superpopulation of stuff. And here is a distribution of change in blood pressure. So in the world in general, in the total population of all the people who suffer from high blood pressure, if they were to receive a drug that works, their blood pressure would change by a certain amount. The majority would change around here, or this amount, and lesser number would change this amount, and so forth. So we have a distribution of the change in blood pressure in the population as a result of this drug, expected by those who assume the drug works. Unsurprisingly, it's normally distributed with a standard deviation of that. Okay. Now the sampling distribution of the mean change, what is that? Do you remember this now? This is if we were to randomly select a sample of people from our superpopulation and then apply our drug and measure the change in blood pressure, and then do so again and again and again an infinite number of times, then each time we're going to get a different change in blood pressure. Most commonly, this is the change in blood pressure we'll find. Least commonly, we'll find changes in blood pressure of this amount and this amount. And this is the case if the n is 1, meaning in each of the samples that we take, we only take one person. So taking one person an infinite number of times, and throwing them back in the pile, and picking another one, and testing their blood pressure an infinite number of times, we get this distribution of their change in blood pressure. That's the sampling distribution of the mean. Remember that? What happens if I take 2 people? Look at that. The distribution got a little tighter. So in this case, I'm selecting 2 people from the general population, giving them the drug, and checking their change in blood pressure, throwing them back in, taking 2 people again, giving them the drug, checking the change in blood pressure, throwing them back in, and doing that infinite number of times until I plot all of the changes in blood pressure I've seen from all my samples, and I get a distribution that looks like that. And if I got an n of 5, oh, look, it's even tighter still. So you see where this is going. The more people I have, the tighter the distribution of the mean change selected from my greater population. All right, so increasing sample size reduces the variability of this mean. Variability is essentially how wide it is. Okay, here we have a standard error. Standard error is standard deviation divided by the square root of the n. As the n gets bigger, this number gets smaller. So the width, the standard error, the width gets tighter and tighter and tighter. So that's visually what's going on when we get more people in our sample. We're getting a tighter splay, tighter, thinner distribution of the variability of the mean change. Okay. So increasing the sample size is like reducing the variance, reducing the width of that distribution. So if we use a more precise measurement method, we can reduce the variance and keep the sample size the same. What does that mean? That means that, let's say we had a better way of measuring blood pressure. Let's say we had a better way of selecting individuals with lesser variability, then we may not need as many people to get the same reduction in standard error. So one way of reducing standard error is to get lots of people. Another way is to get better measurement or a more controlled selection process of my population. So there's a trade-off in cost though. So maybe I'm using the Shoppers Drug Mart brand sphygmomanometer to measure blood pressure. Or I can spend thousands of dollars and get some Doppler radar method of measuring blood pressure. That's not as cheap as just getting more. So a lot of this comes down to money, is I guess the bottom line. So here is our hypothesis test. The intervention has no effect, that's our H naught, and our hypothesis is the intervention changes blood pressure, and we're going to say by at least 10 millimeters of mercury. Now in this case, we have set a difference for measure. That difference is called delta, by the way. So the difference that we hope to detect. And that's kind of important for doing the math that we're going to do later on, is actually defining how we consider a change to manifest. Okay. So let's assume that the drug does not work, that the null hypothesis is true. In other words, the drug does not work. If the drug does not work, and I collect a bunch of samples, and I measure their change in blood pressure, I'm still going to get variability. I'm still going to get some people whose blood pressure changes. And if samples measure the change in blood pressure, I'm still going to get normal distribution of the mean change in blood pressure. But again, assuming that the drug doesn't work, I may actually make a mistake and say that this extreme maybe conclude that in fact it's working, but in fact it doesn't work. That's what we call the rejection zone. That's the type 1 error, right? So here I'm assuming the drug works when it doesn't work. I'm rejecting the null when I shouldn't. That's a type 1 error right there. That's where we get our alpha cutoff. Okay. Now if I'm doing a two-tail test, in the year, just keep that in mind. But in general, okay. So here's what we'll do where it's fine. There should be a curve here. You can move this line further along and make this less errorful. This here is our alpha level. Traditionally, we set our alpha as 0.05, right? Which means that 95% of the cases, I'm not going to make that mistake. But 5% of the cases, I've taken that risk. So hopefully that clarifies some of that alpha p-value stuff we've had in the past. Now let's talk about the type 2 error. So type 2 error is beta. Remember, type 1 was alpha. So when we talk about type 2 error, that in fact the drug type 2 error. So here we go. Let's say here, this curve here, this is the sampling distribution of the mean in the universe where the drug does work. Okay? So in the universe where the drug does work, I'm selecting a bunch of people, I'm giving them the drug, and I'm seeing how much their blood pressure changes. And in fact, the blood pressure changes. Most people are seeing this amount of change, and less people see this amount of change. In the universe where the drug doesn't work, I'm getting a similar distribution because almost all things are normally distributed, but it's not in the same place. Now the difference here, this is delta, the difference between these two means. This is actually that difference that we're looking for, that 10 millimeters of mercury difference that we said we can detect. That's what this represents. Now this, as we mentioned earlier, is our alpha. In this situation, the drug doesn't work, but in this extreme error here, I'm going to say that it does, and I'll be wrong. Where's the type 2 error? In your slide, you will see that the type 2 error is over here. It's under here. Okay? You can't see it on this visualization. Ooh, I have a tweet here. And tweet, the audio is sucking up badly? Well, that sucks. Oh, okay. Let's see if I can fix that. Hey, audio. Let me just go back here for a second. See if I can get the audio fixed a bit. Audio. Okay, hopefully this gets better. I'm speaking more clearly into the microphone, and from my end of things, it looks like I'm recording. So I guess the best I can do is keep going. Boy, this really sucks. It doesn't work. Try again. Okay, so hopefully this will work. If not, well, hey, we'll have to just reconsider. So I'm going to, in addition to talking to you, I'm going to record a separate audio on my phone, and that way we can splice it together later on. Okay, that will solve our problem. So here we go. Right, I am now recording audio on my phone as well. So once again, on your slide, you should. Now, a magical thing. What's going on here? That's really not happening. Okay. The greater the cutoff value for type 1, the bigger the rejection zone. So the bigger the probability of finding a significant effect. Go back here again. So if I move my alpha levels around, I'm getting a greater chance of finding an effect. Okay. Now, as I mentioned, we usually fix. My internet's coming out again. Oh, that sucks. This really sucks with the technology not working. Well, don't worry about it. We'll get through this somehow, and then I will upload the audio, and we'll make it as good as we can get. So we're going to fix the probability at 5%, and the power is 1 minus the our difference between the null and the alternative again. Now, look at that. I've just made my delta bigger, and what's happened to my type 2 error? It's come down. Let's go back again. See, here my type 2 error is huge, and here it got smaller because the difference I was looking for got bigger. Okay, here it's huge, and my type 2 error is small. My type 1 error has not changed at all. So what's the lesson here? The lesson is that I can reduce my type 1 and type 2 errors simply by allowing myself to detect a larger difference. I started out by trying to detect 10 millimeters of mercury. This is like 25 here at this point. So if I'm looking for a bigger difference, I don't need as many people, and I've got less error. The bigger the difference between the mean blood pressures, the more power there is. Okay? Increasing sample size or reducing variance will also increase my power to detect. Now, what happens if I increase sample size? Well, let's try it out. Look at that. So my sample size is doubled, and now I have a little bit less error here. Look at that. There's a lot less error here. Here my sample size has come up by 5. So the lesson there is I can increase the power of my sample by either making the difference I'm looking for larger or increasing the number of people in my sample. So how are we going to compute that? Let us try to use a formula. And the formula I'm going to give you is this. N is 8 times sigma squared, which is the variance, divided by delta squared. And delta is the difference I'm trying to detect. Right? Now, this formula works because we have done the hard work for you. It's actually a very difficult formula to derive. But assuming that my alpha is at 0.05 and my power is 80%, power is 1 minus beta, so beta here is 0.2, okay, then this formula works only in these situations. And only if I'm doing a one sample study. In other words, I got one group of people and I'm looking for a particular difference in their blood pressure change. So let's go through an example. So suppose the standard deviation of the change in blood pressure is about 7 millimeters of mercury. How do I get that? I get that from personal experience or from literature. So the variance is going to be 7 squared, which is 49. We're going to fix our alpha at 0.5 and our power at 80%, and we are going to try to detect a mean difference of 5 millimeters of mercury. That's our delta. Plug it in, and we get 15.68. There's no such thing as 0.68 people, so we always round up. If this was 15.1, we always round up to 16. 16 whole numbers, 16 people. So in other words, I need 16 people in order to detect a change of 5 millimeters of mercury. What if there are two groups? What if I've got a control group and an experimental group? So the control group gets a placebo, and the experimental group gets my drug. This is the more common situation. And the answer isn't that we multiply by 2. It's not. More complicated than that. It's this formula here. It's n per group is 16 times my variance divided by the square of my delta. Remember, this is a requirement per group. And notice this is twice as big as it was in the one group sample. Before it was 8, now it's 16. So the result is 4 times larger than the single group. It's not twice as large, it's 4 times larger. Let's go through an example. So we have our same situation. The standard deviation is going to be 7, so the variance will be 49. Our type 1 is 0.5, type 2 is 0.2, which means 80% power. The difference we're looking for is 5 millimeters per mercury. So we plug it into our formula and we get 31.36. We can't have 0.36 people. We round that up to 32 per group, which means I'm going to need 2 times that for my study. 2 times 32 is 64. That's the hard nuance around this. It's remembering to round up and multiplying by 2. And it's amazing how many will get it bad. So in summary, your sample size increases with greater variance. So the more messy your data, the more people you need. It decreases with increasing delta. So if you are trying to detect a larger thing, you need fewer people. And if you've got lesser error, then you've got lesser sample size requirements. Okay. Now, sample size requirements are going to vary with some other things too. Among them, survival time and things like that. It's going to vary depending upon the type of study you're looking at. These we looked at today were randomized controlled trials. They're pretty comparatively easy to do, but case control or cross-sectional studies, those require different formulas. And other things like what does it cost? And what do my instruments allow me to detect? And how easy is it to include people? That's going to affect practically how we look at the sample size. So that's all for today. In next class, we'll talk about the final exam. So save your questions until then. The final exam is not cumulative, and we'll have a review over what you need to study. I apologize for the cracky internet. Oh God, really not doing these things. And both this and my secondary audio. That is all. Any questions? Please tweet me. Thank you very much, and we'll see you guys later. I'll be broadcast now.